Welcome, AXOR, Galactic Observatory. Tonight, the journey moves gently through the greatest mysteries science still cannot fully explain. From dark matter and black holes to consciousness, dreams alien life, aging, and the strange depths of human nature. This is a quiet voyage across the known universe and into the questions that remain unanswered. Each mystery opens a door into something deeper, revealing how much has been discovered and how much still waits in silence beyond the edge of understanding. This is a place for calm curiosity, slow exploration, and the kind of wonder that makes the universe feel both vast and strangely intimate. If these deep space documentaries and relaxing science journeys speak to your mind, please take a moment to like the video, subscribe to the channel, and join this growing observatory of curious minds. Now, as the night grows still, the story begins with the mysteries that science can describe but not yet solve. Science begins with a simple fact that often feels easy to overlook. Reality is here, space is here, time is here, matter is here. The laws that shape stars, atoms, and living bodies are here. Yet the deepest mystery may be that any of it exists at all. Modern physics can describe the behavior of the universe with extraordinary precision once the universe is already present. It can trace cosmic history back to an early hot and dense state. It can describe how matter formed, how galaxies gathered, and how stars lit the dark. But before all of that, beneath all of that, there remains a question that no telescope, no detector, and no equation has fully answered. Why is there something instead of nothing? It sounds less like a scientific problem than a quiet thought that appears late at night, and yet it touches the foundation of every scientific field. If there were no universe, there would be no particles to measure, no light to observe, no chemistry to study, no life to examine, and no mind to wonder. Everything rests upon the existence of something rather than nothing, and that starting point remains unexplained. In everyday language, nothing sounds simple. It sounds like the absence of all things. But in physics, the idea becomes strangely difficult. What appears empty may not be truly empty. Quantum theory describes a vacuum not as a blank void, but as a state with structure, with fields, with restless activity. Fleeting particles can appear and vanish. Energy can fluctuate. Space that seems still may contain hidden motion. Some physicists therefore suggest that what humans call nothing may never be complete non-being at all. It may instead be a kind of lowest physical state, a thin and unstable background from which something can emerge. Yet this idea, even if it proves useful, does not settle the mystery. A quantum vacuum is already a kind of something. It already assumes laws, fields, and a stage upon which fluctuations can happen. The deeper question remains untouched. Why are there laws? Why are there fields? Why is there a framework in which any physical event can occur? Cosmology carries the story backward toward the earliest known moments. Observations indicate that the universe has been expanding for billions of years. The farther astronomers look into space, the more they also look into the past. That long view reveals a cosmos that was once hotter, denser, and more uniform than it is now. This early state is often called the Big Bang, though the phrase can mislead. It was not simply an explosion in space. It was an expansion of space itself. Galaxies were not flying outward into empty surroundings. Rather, the fabric of the universe was stretching, carrying matter and light with it. The evidence for this picture is strong. Astronomers see the expansion in the shifting light of distant galaxies. They observe the faint cosmic microwave background, the cooled afterglow of an early hot universe. They measure the abundance of light elements that formed in the first minutes. Together, these clues tell a coherent story. Yet even here, where science is powerful, there is a boundary. The Big Bang Theory describes the early development of the universe. It does not fully explain why there is a universe to develop in the first place. It does not reveal with certainty what, if anything, preceded the earliest known state. It does not tell us why expansion began. Many cosmologists think that a brief episode called inflation may have shaped the young universe. Inflation refers to an extremely rapid expansion in the earliest fraction of a second one that could explain why the cosmos appears so smooth on large scales, and why tiny fluctuations later grew into galaxies and clusters. Observations are broadly consistent with this idea, and inflation has become one of the central concepts in modern cosmology. But here again the mystery deepens rather than disappears. What caused inflation? What field drove it? Why did it begin, and why did it end? Different models offer different answers, but no single explanation has been confirmed. In some pictures, inflation may produce many universes, each with different properties, a vast multiverse beyond anything humans can observe directly. That possibility is fascinating, but it also shifts the question rather than closing it. If many universes exist, why does that larger reality exist? Why should there be a multiverse instead of nothing at all? Time itself adds another layer to the puzzle. Human beings experience time as movement, as a steady flow from past to future. Causes come before effects. Memories point backward, not forward. Broken cups do not leap from scattered pieces into a whole shape on the table. Smoke drifts out into a room and does not gather itself back into the flame. Physics, however, is more subtle. Many of its basic laws do not strongly distinguish one direction of time from the other. At small scales, the equations often work in either temporal direction. Yet the lived universe has a clear arrow of time. This arrow is closely tied to entropy, a measure of how energy becomes spread out, and how ordered arrangements tend to give way to more probable disorder. Observations indicate that the early universe had remarkably low entropy, and that unusual condition may help explain why time has a direction at all. But then the question becomes even deeper. Why did the universe begin in such a special low entropy state? Why was the opening condition of reality so ordered that change, memory, aging, and history could unfold from it? No final answer exists. Some thinkers propose that reality may be necessary, that non-existence is not a genuine option, though this remains a philosophical claim more than a scientific result. Others suspect that a deeper theory, perhaps one not yet discovered, will show how space-time, matter and law arise together from something more fundamental. For now, science stands in a remarkable position. It knows an immense amount about what happened after the first moments it can describe, but it does not yet know why there is a universe at all, what truly set the cosmos in motion, or why time opens in one direction, like a river moving through darkness. At the widest possible scale, reality remains a fact more than an explanation. The stars shine inside a framework whose deepest origin is still hidden. Existence itself remains the first and quietest mystery, resting beneath every other question that science has ever asked. Beyond the small islands of light that human eyes can see, the universe appears at first to be a place shaped by visible matter. Stars burn, galaxies turn, clouds of gas drift and collapse, planets circle their suns in quiet paths. For a long time it seemed reasonable to imagine that the cosmos was made mostly of the things that shine, reflect, absorb or scatter light. Yet as astronomy grew more precise, a strange pattern emerged. The universe did not behave as though visible matter was enough. Galaxies rotated too quickly. Clusters of galaxies held together too tightly. Light bent around massive structures more strongly than the seen matter could explain. Again and again, observations indicated that most of the gravitational weight of the cosmos comes from something hidden. This unknown component is called dark matter. The name is simple, but it does not mean that the matter is merely dim or shaded. It means that it does not appear to interact with light in the ordinary ways that familiar matter does. It does not glow. It does not shine by reflection. It does not reveal itself directly through telescopes that study visible light, infrared light, or radio waves. Its presence is inferred through gravity, through motion, and through the way it shapes the large architecture of the universe. One of the clearest clues comes from spiral galaxies. In a simple system ruled only by the mass that can be seen, stars farther from the center should orbit more slowly than stars closer, in much as planets in the solar system move more slowly when they are farther from the sun. But many galaxies do not follow this pattern. Their outer stars move unexpectedly fast, as though they're held by a much larger mass spread far beyond the bright disk. The visible stars, dust and gas, are not enough. A vast hidden halo seems to surround each galaxy, extending well beyond the luminous edge. Clusters of galaxies reveal the same problem on a larger scale. These clusters contain hundreds or even thousands of galaxies bound together by gravity. When astronomers measure how quickly the galaxies move inside a cluster, the speeds suggest far more mass than can be accounted for by stars and gas alone. Even when the hot gas between galaxies is included, most of the needed mass remains unseen. The cluster behaves like a structure whose true weight is largely invisible. Gravitational lensing provides another quiet form of evidence. According to general relativity, mass bends the path of light. A massive galaxy or cluster can act like a lens, distorting the appearance of more distant objects behind it. By studying these distortions, astronomers can map where mass lies even when that mass does not emit light. The resulting maps often reveal broad concentrations that do not match the visible matter alone. Once again, the universe seems to be built around a hidden framework. Dark matter appears not only in individual systems, but in the large-scale pattern of the cosmos itself. Over immense distances, galaxies are not scattered at random. They gather in filaments, clusters, and sheets, separated by great voids. Computer simulations show that this web-like structure forms naturally when dark matter is included. Tiny fluctuations in the early universe grow under gravity, and the hidden matter provides the scaffolding into which ordinary matter later falls. In this picture, stars and galaxies are like lights strung along an invisible architecture. What can dark matter be? That question has remained open for decades. It seems unlikely to be ordinary matter hiding in plain sight. Careful studies of the early universe, especially of the cosmic microwave background and the abundance of light elements, indicate that ordinary matter makes up only a small fraction of the total cosmic content. Dark matter must therefore be something else, a new form of matter not included in familiar atoms. Many candidates have been proposed. Some theories suggest weakly interacting particles that pass through ordinary matter with almost no effect. Others point to lighter particles such as axions that would be extremely difficult to detect. There are also more exotic possibilities involving hidden sectors of physics with particles that interact mainly among themselves. Experiments deep underground search for rare collisions between dark matter and normal matter. Particle accelerators attempt to create hints of it in high-energy events. Telescopes look for indirect signs that dark matter particles might occasionally destroy one another and produce detectable radiation. So far, none of these efforts has delivered a final and universally accepted answer. The evidence for dark matter's gravitational effects remains strong, but its true identity remains hidden. Some scientists have asked whether the mystery points not to unseen matter, but to an incomplete understanding of gravity. Perhaps gravity behaves differently over large distances or in weak fields. Modified theories have been proposed and in some cases can explain certain galactic motions. Yet across the full range of evidence, especially in clusters, gravitational lensing, and the large-scale structure of the universe, dark matter remains the more widely supported explanation. Still, the discussion continues because science advances not by comfort, but by careful tension between evidence and interpretation. The mystery deepens further when dark matter is placed beside dark energy. If dark matter concerns missing mass that helps pull structures together, dark energy concerns a different and even stranger effect. Observations of distant supernovae along with other cosmological measurements indicate that the expansion of the universe is speeding up. Instead of slowing under gravity alone, cosmic expansion appears to be accelerating. To account for this, cosmologists use the term dark energy, which may represent a property of space itself or some new field that acts across the universe. In the current standard, picture ordinary matter makes up only a small share of the cosmos. Dark matter contributes much more. Dark energy contributes more still. That means the matter humans know the matter in stars, oceans, rocks, bodies, and air is only a thin, visible fraction of reality. Most of the universe is made of components that remain poorly understood. There is something deeply humbling in this. Human beings learn to measure planets, split atoms, decode genes, and detect waves in space-time, and yet when they add up the universe, they find that the familiar world is a minority. The greater part remains unseen, known mostly through its influence. Dark matter does not announce itself with color or shape. It reveals itself by what it holds, by how it bends, by the motions it permits and the motions it restrains. It is present in the turning of galaxies, in the binding of clusters, in the ancient pattern left by the early universe, and in the hidden framework beneath the visible sky. Science has measured its effects with increasing confidence, but not its essence. The cosmos appears full of invisible structure, as though lighted matter drifts within a deeper and darker design. For now, dark matter remains one of the clearest signs that the universe is larger than the part it chooses to show. Once the hidden matter of the universe comes into view, another mystery begins to take shape behind it. The cosmos does not merely exist. It also appears to be strangely well arranged for complexity to arise within it. Stars can form, atoms can remain stable, elements can be forged inside stellar cores and scattered into space. Planets can gather from dust. Chemistry can grow intricate. Life, at least in one known corner of the universe, can emerge from matter and persist long enough to wonder about its own origin. None of this had to happen in an obvious way. The laws of physics contain certain fixed values, often called constants, that set the strength of forces and the behavior of particles. If some of these values were even modestly different, the universe might look nothing like the one now observed. This has led many scientists and philosophers to reflect on a difficult and unsettling question. Why do the laws and constants of nature seem to fall within such a narrow range that allows structure, stars, and living systems to exist at all? The question is often described as fine-tuning. The phrase does not prove that the universe was designed, and in science it is not used as proof of intention. It refers instead to a pattern that appears surprising. The basic rules of nature seem delicately balanced. Gravity, for example, is weak compared with other forces, yet if its strength was substantially different, the lives of stars would change dramatically. A much stronger gravity might cause stars to burn too quickly or collapse too easily. A much weaker gravity might make it difficult for stars to form at all. The electromagnetic force must also lie within a range that allows atoms to hold together and chemistry to function. The strong nuclear force binds protons and neutrons inside atomic nuclei. If it were altered too much, the familiar elements of matter could become rare, unstable, or impossible. The masses of basic particles matter as well. The proton, neutron, and electron must stand in a certain relationship for atoms, molecules, and stable matter to exist in the forms now known. Even the cosmological constant, which is associated with the energy of empty space and the expansion of the universe, appears to fall within a remarkably narrow range. If it were much larger in a positive direction, space might expand so rapidly that matter could never gather into galaxies. If it were very different in the other direction, the universe might collapse too soon. These examples do not mean that life in any form is impossible under all alternate laws. Science cannot survey all possible realities, but they do suggest that the universe humans inhabit rests within a special region of possibility where long-lasting structure can emerge. The mystery becomes more vivid when it is viewed not through abstract numbers alone but through consequences. A universe without stable stars would have no long slow furnaces to create heavier elements. A universe without carbon chemistry or something similarly rich might struggle to build complex molecules. A universe expanding too violently would remain thin and scattered. A universe collapsing too quickly would never allow long histories to unfold. The observed cosmos seems to stand in a narrow corridor where order, change, and complexity can coexist. There are several broad ways thinkers respond to this. One possibility is that the appearance of fine-tuning reflects a deeper theory not yet discovered. In this view, the constants may not be arbitrary at all. They may emerge inevitably from a more fundamental set of laws. What now looks like a delicate balance could one day seem as natural as the shape of a crystal, emerging from its deeper molecular order. This approach appeals strongly to many physicists because it seeks explanation rather than acceptance. It assumes that apparent coincidence may hide a deeper necessity. Another possibility is linked to the idea of a multiverse. If there are many universes or many large regions with different physical properties, then it is less surprising that at least one of them would have the right conditions for observers to arise. In such a picture, humans do not find themselves in a life-friendly universe because that universe is uniquely chosen. They find themselves there because only such a universe can host beings capable of asking the question. This is related to what is called the anthropic principle, the observation that any universe observed by conscious beings must permit the existence of conscious beings. In its simplest form, this is almost a statement of selection. It does not tell why the universe is life-permitting, only why observers should not be surprised to find themselves in such a place. Some scientists find this helpful as a reminder against false astonishment. Others feel it leaves the deeper question unresolved. A selection effect may explain why observers notice certain conditions, but it does not fully explain the origin of those conditions themselves. The multiverse idea also faces a serious difficulty. It remains uncertain whether other universes can ever be observed or tested in a direct way. Some multiverse concepts arise naturally from certain inflationary models or from some interpretations of fundamental physics, but at present there is no decisive empirical confirmation. That does not make the idea worthless, but it keeps it on uncertain ground. Science prefers explanations that can be constrained by evidence, and here the evidence remains incomplete. There is also the more philosophical possibility that the constants simply are what they are without deeper reason accessible to human inquiry. This possibility is unsatisfying to many minds because it halts the search. Yet nature does not promise to be easily interpretable. Some facts may ultimately be brute facts, basic features of reality that can be described but not further reduced. Whether fine-tuning belongs in that category is unknown. The puzzle remains suspended between mathematics, cosmology, and philosophy. It touches a deeper emotional current as well. Human beings often expect reality to feel either chaotic or inevitable. Fine-tuning suggests something stranger. The world looks contingent, as though it might easily have been different, and yet it also looks strangely hospitable to complexity. It is neither obviously random in its consequences nor clearly explained in its foundation. Stars live long enough to warm planets. Matter organizes into patterns of astonishing richness. Conscious minds appear within a universe governed by silent numerical relations that seem balanced on an invisible edge. Science can measure these values with extraordinary skill. It can calculate what follows from them. It can model alternate outcomes when they are changed. But it cannot yet say with confidence why these values take the form they do. The laws of nature do not merely permit existence. They permit a particular kind of existence, one in which light can gather around matter. Chemistry can become history, and the universe can slowly awaken into self-awareness. Whether this balance points to deeper necessity, vast unseen multiplicity, or an unanswered fact at the heart of nature remains one of the quietest and most profound mysteries in science. After the laws and constants of nature are considered, the mystery of the universe opens outward again into questions of scale, shape, and limit. Even if the visible cosmos can be described with growing precision, it remains uncertain how much of reality is actually within reach of observation. Human beings look into space with telescopes that gather faint light from distant galaxies, and they build maps of the cosmos that stretch across unimaginable distances. Yet every map ends, not because reality necessarily ends, but because light has had only a finite time to travel. The universe has a history, and that history places a horizon around what can be seen. Beyond that horizon there may be more of the same cosmic structure, or something very different, but the boundary of observation remains firm. This alone gives rise to one of the deepest questions in cosmology. How large is the universe beyond the part that can be observed, and does it have an edge, a shape, or a total form that lies forever beyond direct view? The observable universe is not the whole universe in any guaranteed sense. It is the region from which light or other signals traveling at the speed limit of nature has had time to reach Earth since the beginning of cosmic expansion. Because the universe has a finite age, there is a finite distance from which information can arrive. This creates a cosmic horizon. It is not a wall made of matter. It is not a shell marking the end of space. It is simply the limit of what can be seen from one location at one moment in cosmic time. If observers stood in a distant galaxy, they too would have an observable universe centered on themselves with its own horizon. This means that the unseen universe beyond the human horizon may be enormous, perhaps vastly larger than the visible part, perhaps even without end. Whether space is infinite remains unknown. Observations indicate that on the largest scales accessible to measurement, the universe is very nearly flat in its geometry. In ordinary language, flat here does not mean empty or featureless. It refers to the large-scale behavior of space itself. In curved space, parallel lines might eventually converge or diverge. In flat space, they remain parallel in the ideal geometric sense. Measurements of the cosmic microwave background and the distribution of matter suggest that the universe is close to flat, but close is not the same as exact. The true geometry might be perfectly flat and infinite, or only so close to flat that its full curvature lies beyond observational reach. A very large curved universe could appear flat within the small patch that human instruments can examine. This leaves open several possibilities. Space may extend forever in all directions. It may be finite but unbounded, wrapped in a higher dimensional geometry, somewhat as the two-dimensional surface of a sphere is finite, yet has no edge for a being confined to the surface. Or it may have some even stranger global form that cannot be easily pictured with ordinary intuition. The possibility of a finite but edgeless universe often feels strange, because human thought expects limits to look like boundaries. A room ends at walls, a field ends at a fence, a map ends at a border. But geometry allows a different kind of completion. A creature walking on a sphere can continue forever, without finding an edge, eventually returning to the starting point. If three-dimensional space has an analogous form, then the universe could be finite without presenting any visible wall or outer rim. So far, however, there is no decisive evidence that space closes back on itself in this way. Searches for repeating patterns in the sky, which might suggest that light has wrapped around a finite cosmos, have not produced a confirmed result. Once again, the evidence narrows possibilities without delivering final closure. Another mystery concerns what lies beyond the observable horizon, not just in distance but in principle. Inflationary cosmology suggests that the region humans can see may be only a tiny patch of a much larger expanse. During inflation, space may have expanded so quickly that the small region now observable is like a single calm area within a vast and perhaps unimaginably larger reality. If so, the structures visible in the night sky are only a local sample. Beyond them could lie more galaxies, more clusters, more dark matter halos, and perhaps conditions that differ in subtle or dramatic ways. Yet because light from those regions has not reached Earth, and may never do so, they remain inaccessible to direct test. Science can model such possibilities, and in some cases it can infer them indirectly from theories that explain observed features, but the distance between inference and observation remains important. The boundary of the observable universe marks not just a practical limit, but an epistemic one, a limit on what can be known by direct inspection. There is also the question of whether the universe has a beginning boundary in time that corresponds to a boundary in knowledge. The earliest light now visible comes from the cosmic microwave background released when the universe cooled enough for atoms to form and light to travel freely. Before that time, the cosmos was opaque. Earlier conditions must be inferred through theory and indirect evidence. This means that even within the observable universe there are layers hidden behind physical veils. Reality is not equally transparent across all epochs. Some chapters can be seen with relative clarity. Others must be reconstructed from traces. The deeper science moves toward origin, the more it encounters horizons of one kind or another. Some are limits of light, some are limits of energy, some are limits of theory itself. The idea of an edge also invites a simpler but still powerful question. What is the universe expanding into? In common imagination, expansion suggests an object growing into surrounding emptiness. But in standard cosmology, the universe is not expanding into an external space that observation has revealed. Rather, space itself is expanding internally. Distances between large-scale structures increase because the fabric relating those distances changes. This is difficult to picture because the human mind prefers containers and contents. Yet the cosmos may not sit inside a larger room in any familiar sense. Whether there is some wider framework beyond space-time remains unknown. Current cosmology does not require such a container in order to describe observed expansion. It simply describes how space changes within the universe itself. The result is a vision of reality that is both measured and incomplete. Human beings know the age of the observable universe to remarkable precision. They know how cosmic structures formed across vast spans of time. They know that the visible cosmos is homogeneous on very large scales and richly clumped on smaller ones. But they do not know the total size of all that exists. They do not know whether space is truly infinite, gently closed, or shaped in a way no everyday image can capture. They do not know what lies forever beyond the horizon, or whether the horizon encloses only a small local fragment of something immensely greater. The universe reveals enough to inspire confidence in its order, yet withholds enough to preserve wonder. Its farthest reaches remain less like a finished map than a coastline fading into mist, where observation ends and possibility continues. Beyond the largest structures of the universe, beyond galaxies, dark matter halos, and the visible horizon, the path inward eventually reaches a region where ordinary intuition begins to fail completely. On these smallest scales, nature does not behave like the solid and continuous world of daily experience. It behaves in ways that are precise in mathematics, powerful in prediction, and deeply resistant to simple understanding. This is the quantum world where particles can act like waves, where outcomes are described by probabilities, and where measurement itself seems woven into the behavior of reality. Quantum theory is one of the most successful frameworks in all of science. Its predictions have been tested with extraordinary accuracy. It underlies modern electronics, lasers, atomic clocks, and much of present-day physics. Yet despite this success, its meaning remains unsettled. It explains what happens, but not in any way that feels fully comfortable. At the heart of quantum theory lies the idea that physical systems are described by a spread of possibilities rather than a single definite state before measurement. A particle such as an electron is not always best pictured as a tiny bead moving along a fixed path. In many situations, it is described by a wave function, a mathematical object that encodes the probabilities of different outcomes. This does not mean the particle is only ignorance in disguise, as though it secretly has a definite path that humans simply do not know. Experiments suggest something stranger. Nature itself may remain genuinely indefinite in certain respects, until an interaction occurs that selects one result from several possibilities. The famous double-slit experiment offers one of the clearest windows into this strangeness. When particles pass through two narrow openings and are not observed in a way that reveals which slit each one uses, they create an interference pattern, a pattern associated with waves overlapping. It is as if each particle behaves like a spread-out possibility, moving through both paths at once. But when a measurement is made that determines which slit was used, the interference pattern disappears. The behavior changes depending on the information that becomes available. This is not merely an odd technical detail. It suggests that the world at small scales does not possess ordinary classical properties in a simple and observer-independent way. Superposition is the term often used for this condition. A system can exist in a combination of possible states at once until an interaction yields a definite outcome. In everyday life, objects appear settled. A cup is on the table or it is not. A lamp is on or off. But quantum systems can occupy combinations that have no obvious classical equivalent. This leads to one of the central unresolved questions in physics. What exactly causes a quantum possibility to become a single observed reality? Standard calculations treat measurement as a special moment, but the nature of that moment remains controversial. Some interpretations say the wave function truly collapses into one outcome. Others say there is no collapse, only branching realities in which every allowed outcome occurs in different parts of a larger structure. Still others attempt to explain the appearance of collapse through decoherence, the process by which a quantum system becomes entangled with its environment and loses the delicate phase relations that allow superposition to remain visible. Decoherence explains much about why the everyday world appears classical. Tiny quantum effects are easily washed out by contact with the wider environment, yet decoherence alone may not settle the deeper question of why one experienced outcome is seen rather than another. Entanglement carries the mystery even further. When two particles interact in certain ways, their properties can become linked so deeply that they must be described as parts of one combined system, even when separated by large distances. Measuring one particle immediately constrains what can be found about the other. This does not allow useful signals to travel faster than light, and so it does not violate relativity in that practical sense. But it does reveal that quantum reality is not built from entirely independent local parts, in the way classical intuition suggests. The world seems to possess relations that are more fundamental than separateness. Experiments testing Bell inequalities have shown that no simple local hidden variable picture can reproduce all quantum predictions. The universe at small scales appears genuinely non-classical. Another mystery lies in the role of probability. In classical uncertainty, probability usually reflects ignorance. A coin under a cup is already heads or tails even before it is revealed. In quantum theory, probability seems more intrinsic. The formalism predicts only the chances of different outcomes. Why nature should be built this way remains unclear. Some interpretations treat the probabilities as basic. Others attempt to derive them from branching worlds or deeper statistical principles. None has won universal agreement. Time in the quantum world is also unsettling. The equations often evolve smoothly and reversibly, while measurement seems abrupt and irreversible. This creates a conceptual divide between the gentle unfolding of the wave function and the sharp definiteness of observation. Physics can use both ingredients with remarkable effectiveness, yet the join between them remains philosophically and perhaps physically incomplete. The problem is not that quantum theory fails in experiment. The problem is that its formal power exceeds the comfort of human understanding. Even the question of what counts as an observer remains uncertain. Must a conscious mind be involved in measurement? Most physicists would say no. An interaction with a measuring device or environment is enough to produce effective definiteness. Yet the history of the subject has kept the language of observation close to the center, and this has encouraged generations of debate about whether reality is fully defined before it is measured. At present, no consensus interpretation has dissolved all difficulty. Some scientists take a practical stance and focus only on prediction, holding that the theory works and that metaphysical discomfort is secondary. Others believe the conceptual problems point toward a deeper layer of physics still to be found. Quantum theory therefore stands in a rare position. It is both complete in its predictive reach across many known domains and incomplete in its interpretation. It tells matter how to behave, but not in a language that easily matches ordinary human pictures of reality. The small-scale world seems to shimmer with potential, rather than fixed form, with connection rather than separation, and with outcomes that emerge from probability rather than mechanical certainty. Beneath the solid surfaces of daily life lies a deeper order that is not disorder, yet not the kind of order the human mind first expects. Science has learned to calculate within this realm with extraordinary success, but what quantum reality truly is remains one of the most profound unanswered questions in all of physics. As the quantum world gives way to larger structures, another mystery rises from beneath it, one that has shaped physics for more than a century and still resists completion. The universe appears to be governed by two grand frameworks that both work with astonishing power, yet they do not fit together in any final and seamless way. One is quantum theory, which describes matter and forces at very small scales with extraordinary accuracy. The other is general relativity, which describes gravity, space, and time on large scales, from falling objects to orbiting planets to expanding galaxies. Each theory has transformed human understanding. Each has passed difficult experimental tests. Yet when both are required at once, especially in the most extreme conditions, they resist union. Nature seems to speak in two deep languages, and science has not yet found the complete grammar that contains them both. General relativity presents gravity not as a force in the ordinary sense, but as the curvature of space-time. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Planets circle stars not because they are pulled through empty space by an invisible rope, but because they follow natural paths through a geometry shaped by mass and energy. This picture explains the motion of Mercury, the bending of light near the Sun, the existence of black holes, and the expansion of the universe itself. It has survived every major test applied to it across a vast range of scales. Yet relativity is a classical theory. It treats space-time as smooth, continuous, and well-defined. Quantum theory, by contrast, is built on uncertainty, probability, and discrete interactions. It treats fields and particles in ways that often imply fluctuations, even in vacuum states that appear empty. These two styles of description become difficult to reconcile when gravity enters domains where quantum effect should matter strongly. This happens in places of enormous density and tiny scale, such as the earliest moments of the universe or the deep interior of black holes. There, the smooth space-time of relativity may no longer remain smooth. Quantum fluctuations may become inseparable from the geometry itself. But the standard equations do not yet yield a complete and empirically confirmed theory of quantum gravity. One clue to the mystery lies in gravity's peculiar weakness. Of the known fundamental interactions, gravity is by far the weakest in ordinary circumstances. A small magnet can lift a metal clip against the pull of the entire Earth. Electric forces between tiny charged particles can vastly exceed their gravitational attraction, yet gravity dominates the large-scale architecture of the universe because it is always attractive and acts over great distances. This raises a profound question. Why is gravity so weak compared with the other forces? No final answer exists. Some proposals suggest that gravity may spread through extra dimensions beyond the familiar 3 dimensions of space, diluting its apparent strength. Others seek an explanation in the structure of quantum fields or in deep features of space-time itself. For now, gravity's weakness remains one of the quieter symmetries built into nature. The challenge of unification is not merely technical. It suggests that one or both of the current frameworks may be incomplete descriptions of a deeper order. Quantum field theory successfully describes 3 of the known interactions within a shared mathematical approach, and the standard model of particle physics stands as one of the most accurate achievements in science. Yet gravity remains outside that structure in a full sense. When physicists attempt to treat gravity like the other forces in a straightforward quantum way, the calculations often produce infinities that cannot be controlled by the same methods that work elsewhere. This is a sign not necessarily of failure but of missing foundations. It may mean that space-time is not fundamental in the form humans now describe it. It may mean that gravity emerges from deeper microscopic relations, much as temperature emerges from the motion of countless molecules, rather than existing as a basic ingredient by itself. Several major approaches try to move beyond this impasse. String theory proposes that the basic constituents of reality are not point-like particles, but tiny vibrating strings whose modes of vibration correspond to different particles and forces. In this framework, gravity appears naturally, and extra dimensions often arise as part of the mathematics. The theory is rich, ambitious, and mathematically powerful, but it has not yet produced decisive experimental confirmation. Loop quantum gravity takes a different path, suggesting that spacetime itself may have a discrete structure at the smaller scales woven from quantum loops or networks. In this view, space may not be continuous all the way down, but built from tiny units with geometric relationships. This approach also remains incomplete and unconfirmed in its observable consequences. There are other ideas as well, including proposals that space-time and gravity emerge from entanglement information or thermodynamic principles. These efforts hint at a future in which geometry is not the starting point, but the visible result of something deeper. Black holes in the early universe make the need for such a theory especially clear. In black holes, relativity predicts singularities, places where curvature becomes infinite, and known physics breaks down. In the earliest known cosmic moment, the universe may also trace back toward an apparent singular beginning. Most physicists suspect that infinities of this kind are not literal features of nature, but signs that current theories have reached their limit. A complete quantum theory of gravity might smooth replace or reinterpret these singular states. It might explain what happens where ordinary spacetime concepts fail. It might reveal whether time itself has a beginning in the way humans imagine, or whether the language of beginning is too crude for the deepest structure of reality. There is also a subtle philosophical tension between the two great theories. Relativity is geometric and continuous, built on the shape of spacetime. Quantum theory is algebraic and probabilistic, built on operators, amplitudes, and possibilities. One feels like a description of the stage, the other feels like a description of the actors. But perhaps this division is itself misleading. Perhaps the stage and actors arise together from something more basic than either geometry or particle. Science has not yet reached that layer with confidence. For now, physics lives with a beautiful fracture at its core. It possesses two magnificent maps of reality. One governs the vast, one governs the tiny. Both are true within their domains. Both reveal the hidden order of nature with unmatched precision. Yet where the deepest gravity meets the deepest quantum uncertainty, the maps no longer overlap cleanly. The search for unification is therefore more than a search for a better equation. It is a search for the underlying shape of reality itself, a search for the level at which space-time, matter, and law no longer stand apart. Until that level is found, gravity remains not only the force that shapes stars and galaxies, but also one of the clearest signs that human understanding is still incomplete. Where relativity and quantum theory fail to join, cleanly black holes emerge as the most severe test of both. They are not merely exotic objects scattered through distant space. They are regions where the known laws of physics are pushed toward their deepest limit, where gravity becomes so intense that ordinary descriptions of matter, light, and time begin to strain. Black holes were once treated as strange mathematical possibilities, hidden inside Einstein's equations, perhaps too extreme to exist in nature. Now they are understood to be real and common. Astronomers observe stars orbiting invisible masses at galactic centers. They detect powerful X-ray emissions from matter heating as it falls inward. They record gravitational waves from black holes colliding in distant galaxies. In recent years, telescopes have even produced shadow-like images of the hot, glowing material surrounding supermassive black holes. The existence of these objects is no longer seriously in doubt. What remains uncertain is what they truly are at the deepest level, and what they reveal about the structure of reality itself. A black hole begins when matter is compressed into a region dense enough that gravity overwhelms every known resisting force. In the simplest picture, there is an event horizon, a boundary beyond which nothing that follows ordinary paths can return to the outside universe. Light emitted inside this boundary cannot climb back out. Signals cannot escape. The horizon is therefore not a solid surface in the usual sense, but a one-way limit in space-time. To an outside observer, it marks the edge of causal separation. This alone is strange enough, but relativity carries the picture further inward. According to the classical equations, matter that continues collapsing past the horizon is driven toward a singularity, a region where density and curvature become infinite, and the known description of space-time breaks down. Most physicists do not regard this infinity as a final feature of nature. It is more likely a sign that the theory has been extended beyond the domain where it can remain complete. Yet until a successful theory of quantum gravity is established, the singularity remains a symbol of unfinished understanding. Time around a black hole behaves in ways that challenge human intuition. General relativity predicts that clocks run differently in strong gravitational fields. Near a black hole, time slows relative to observers farther away. This effect is not an illusion of faulty measurement. It is built into the geometry of space-time itself. An outside observer watching matter fall toward the horizon may see the process appear increasingly slowed and dimmed, as though the infalling material never quite crosses the boundary. Yet for the falling matter itself, crossing the horizon may occur in finite proper time, with nothing especially dramatic at the exact boundary in the case of a sufficiently large black hole. These two descriptions are not contradictions. They reflect the different paths through space-time followed by different observers. Black holes therefore challenge not only matter and light, but also the human habit of assuming one shared universal time. The mystery deepens when quantum theory is brought into the picture. For many years, black holes were thought to be perfectly black, swallowing matter and energy, while emitting nothing. Then Stephen Hawking showed that quantum effects near the horizon should allow black holes to radiate faintly. In simple terms, the vacuum near the horizon is not empty in the classical sense. Quantum fields fluctuate, and the curved space-time near the horizon changes how these fluctuations behave. The result is Hawking radiation, a slow leakage of energy that causes black holes to lose mass over immense spans of time. This was a profound shift. Black holes were no longer permanent prisons. They could at least in principle evaporate. Yet this insight produced a deeper puzzle known as the black hole information problem. In quantum theory, information about a physical system is not supposed to vanish completely. Even when matter changes form, the underlying evolution is expected to preserve the full quantum description. But if a black hole forms from matter in a specific quantum state, and later evaporates into apparently featureless thermal radiation, what happens to the information about what fell in? Does it disappear? Is it somehow encoded in the radiation in a way not yet fully understood? Does it remain trapped forever in a remnant? Or does the very framework of space and time need revision to answer the question properly? This is not a minor technical issue. It touches the consistency of physics at a foundational level. If information can truly be destroyed, then quantum theory may require alteration. If it cannot be destroyed, then the classical picture of black holes may be incomplete in some essential way. Over the years, many ideas have been proposed. Some suggest that information is subtly encoded in Hawking radiation, though recovering it may be fantastically difficult in practice. Others suggest that the event horizon is not as smooth as classical relativity implies, but possesses a more active or structured quantum character. Concepts such as holography have transformed the debate. The holographic principle suggests in broad terms that the information content of a region of space may be describable by degrees of freedom associated with its boundary rather than its volume. This idea arose partly from black hole thermodynamics, where the entropy of a black hole appears proportional to the area of its horizon, not the volume enclosed. That result is deeply strange. It hints that space-time and gravity may be governed by informational rules unlike those of ordinary intuition. Some of the strongest theoretical work in modern physics suggests that gravity in certain kinds of space can be equivalent to a lower dimensional quantum theory without gravity on a boundary. These insights have not yet solved every real astrophysical question about black holes, but they strongly suggest that black holes are not merely cosmic traps. They may be windows into the way reality stores information at its deepest level. There are still further mysteries. Astrophysical black holes appear in a vast range of sizes, from the remnants of massive stars to the supermassive giants in galactic centers. Some of those giant black holes existed surprisingly early in cosmic history, growing to enormous masses faster than many formation models easily explain. Their spin, their feeding history, and their role in shaping galaxies remain active areas of study. At the very center of the mystery, however, lies the unseen interior. No observation directly reveals what occurs beyond the horizon. The interior remains hidden not because instruments are weak, but because the structure of causality itself denies outward report. Science can infer, calculate, and compare theories, but the deepest region stays sealed from direct testimony. Black holes therefore stand at a rare intersection. They are measurable and hidden, predicted and unresolved, real in astronomy and incomplete in theory. They unite gravity, quantum uncertainty, thermodynamics, and information in one severe problem. They show that the universe contains places where space folds inward so completely that not even light can return, and where human understanding approaches a similar horizon. The study of black holes has already changed physics more than once. It may yet change it again, because inside these dark regions the universe seems to guard clues about time information and the very fabric of existence. Beyond the hidden interiors of black holes, the universe opens again into a different kind of mystery, one written not in darkness alone, but in the first visible structures that rise from it. After the early universe cools from its original hot and dense state, matter begins to gather under gravity. Tiny fluctuations in density preserved from the young cosmos slowly grow. Regions with slightly more matter pull in more matter. Over immense spans of time, the first stars ignite, the first galaxies assemble, and the large-scale cosmic web begins to take on the shape that later telescopes will observe. In broad outline, this story is one of the great successes of cosmology. Yet when astronomers look closely at the earliest luminous structures, they find important gaps in understanding. The transition from a nearly smooth early universe to a richly structured cosmos remains only partly explained. The first lighted objects do not simply appear as expected. Some emerge too early, some grow too fast, and some possess forms whose origins are still uncertain. The first stars are among the quietest missing chapters in the cosmic record. These stars form before the universe contains the wide range of heavy elements that later generations inherit. In astrophysics, elements heavier than hydrogen and helium are often called metals, and the first stars are thought to have formed from almost pure primordial material. Without heavier elements to help gas cool efficiently, the process of collapse may have worked differently from the way it does in later star-forming clouds. Many models suggest that the first stars were unusually massive, hot and short-lived. They may have burned quickly, flooded their surroundings with harsh radiation, and ended in violent explosions or direct collapse into black holes. Yet no first-generation star has been observed directly with full certainty. Their existence is strongly expected, but their exact masses, lifetime's distribution and role in shaping subsequent cosmic history remain active questions. One of the key transitions in early cosmic history is reionization. After the universe cools enough for neutral atoms to form, space becomes dark in visible terms, filled with gas that no longer glows like the earlier plasma. Later, the first luminous objects begin to emit energetic light that strips electrons from hydrogen, once again gradually transforming the intergalactic medium. This process, called reionization, changes the state of the universe on vast scales. Observations suggest when this broad transition occurs, but not every detail of how it unfolds. Which sources provide most of the ionizing light? Are the first stars enough? Do early galaxies dominate? Do accreting black holes contribute more than once thought? The timing and patchiness of reionization continue to be studied, and each new observation helps refine a story still incomplete. Early galaxies themselves present further puzzles. Telescopes looking far back in time reveal galaxies that already appear surprisingly developed. Some show substantial masses and organized structures earlier than many models once predicted. As instruments improve, especially in infrared astronomy, the early universe seems increasingly crowded with objects that become visible not long after the first stars should have formed. This does not mean cosmology has failed, but it does mean that the efficiency of early galaxy formation, star formation, and matter assembly may need continued revision. The young universe may have been better at building luminous structure than older assumptions allowed. Spiral galaxies raise another long-standing mystery. In the nearby universe, spiral arms are among the most recognizable large-scale patterns in astronomy, sweeping outward in elegant forms from galactic centers. Yet the exact reason these structures persist remains subtle. They are not static painted stripes made of the same stars forever fixed in place. Stars move through the galaxy, and if the spiral pattern were simply material, wound up by rotation, it would quickly become too tightly wrapped to resemble what is observed. Instead, many astronomers understand spiral arms as density waves, or recurring gravitational patterns regions where matter is compressed as it moves through the galactic disk. This broad picture helps, but the formation, longevity, and variation of spiral structure are still not fully settled. Barr's interactions with nearby galaxies' dark matter distributions, gas flows, and feedback from star formation may all play roles. The visible elegance of a spiral galaxy hides a dynamic system not yet completely understood. Even more striking is the mystery of early supermassive black holes. Observations reveal quasars, intensely bright objects powered by accreting black holes already present when the universe is still young. Some of these black holes reach enormous masses far earlier than many standard growth models easily explain. To grow a black hole of such scale, matter must fall inward efficiently, and for long enough, yet early cosmic time is limited. Did these giants begin from unusually massive seeds formed by direct collapse of gas clouds? Did they grow through bursts of rapid accretion more effectively than expected? Did mergers among early structures accelerate the process? The answers remain uncertain. These ancient black holes are especially important because they show that some of the most extreme objects in the universe become established very early, suggesting that cosmic structure formation is not only gradual, but in some cases startlingly swift. There are also the largest structures of all the filaments, walls, and voids of the cosmic web. Standard cosmology describes their emergence from early density fluctuations, amplified by dark matter and expansion, and on the whole this framework works well, Yet certain observed features continue to invite scrutiny, including the distribution of satellite galaxies around larger hosts, the internal structure of dark matter halos, and tensions in how small-scale cosmic structures compare with simulations. Some of these issues may reflect incomplete astrophysical modeling rather than failures of cosmology. Gas dynamics, stellar feedback black hole outflows, and observational bias complicate the picture. Still, the fine details of how structure forms from primordial fluctuations into the rich and varied cosmos now seen remain an area where theory and observation continue to sharpen one another. What makes these early structures so compelling is that they stand at the threshold between simplicity and complexity. The early universe begins almost uniform with tiny fluctuations that can be measured in the cosmic microwave background. From those faint irregularities arise all later forms, stars, galaxies, clusters, planets, chemistry, and life. The fact that so much complexity can emerge from such slight beginnings is one of the most remarkable features of nature. Yet the exact route from first fluctuation to first star, from first gas cloud to first luminous galaxy is not fully mapped. Some stages are hidden by distance. Some are blurred by limited data. Some depend on physical processes that are hard to simulate in full detail across enormous ranges of scale. Science therefore knows the broad arc of cosmic dawn, but many of its first bright chapters remain unfinished. The ancient sky is not silent. It carries traces of first light in radiation, in elemental abundances in distant galaxies, and in the masses of black holes that appear earlier than expected. But those traces do not yet close the story. The earlier structures of the universe remain a frontier where observation improves quickly, theory adapts constantly, and the cosmos still withholds part of its memory. As the first structures of the universe settle into stars, galaxies, and growing black holes, the sky begins to produce signals of extraordinary violence and mystery. Some arrive as brief flashes, some pulse with uncanny regularity, some crash into Earth's atmosphere carrying energies far beyond anything human machines can generate. These events are not quiet background details of the cosmos. They are among the most energetic and extreme phenomena known, and yet many of them remain only partly understood. The universe does not simply shine. It also erupts, spins, bursts, and sends messages across immense distances in forms that still resist full explanation. Among the most puzzling of these signals are fast radio bursts. These are extremely brief flashes of radio waves, often lasting only a fraction of a second. Yet during that tiny interval, they can release an enormous amount of energy. For many years they appeared as rare and isolated events difficult to trace and harder still to explain. As more instruments began to search for them, the number of known bursts increased rapidly. Some were found to repeat. Others appeared only once. Their sources were located in distant galaxies, sometimes in star-forming regions, sometimes in more complex environments. The fact that some fast radio bursts repeat and others do not suggests that more than one mechanism may be involved, or that one class of objects may behave in different ways under different conditions. One leading idea connects many of these bursts to magnetars, a special kind of neutron star with an immensely strong magnetic field. Neutron stars themselves are already extreme. They are the collapsed cores left behind after certain massive stars die. Packed into a sphere only about the size of a city, they hold more mass than the Sun, in a state so dense that ordinary atomic structure is no longer intact in familiar form. A magnetar adds another layer of severity. Its magnetic field can be so intense that it reshapes the behavior of matter and radiation around it. Observations from within the Milky Way have shown that at least one magnetar can produce radio bursts resembling the weaker end of the fast radio burst population, making this connection especially compelling. Yet not every observed property of fast radio bursts is fully explained, and the full range of source types remains uncertain. The puzzle is not only what object produces them, but how such short, bright bursts are generated with such apparent efficiency. Pulsars offer a different kind of cosmic rhythm. These are rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, the beam sweeps through space. If Earth lies in the path of that beam, the signal arrives in regular pulses like the beam of a lighthouse seen from a distance. When pulsars were first discovered, their steady timing was so surprising that the signals were briefly considered by some as possible evidence of intelligent origin, though this idea was quickly set aside. Pulsars are now understood as natural objects, but they remain scientifically rich because of their precision and their extremity. Some spin astonishingly fast. Some orbit companions in tight systems that allow tests of relativity. Some suddenly change their spin rate in events called glitches, which may reveal the strange internal physics of neutron star matter. Deep inside these objects, matter is compressed to densities beyond those found in atomic nuclei, and it remains uncertain exactly what state it takes there. The surface signal is clear, but the inner substance remains hidden. Cosmic rays add yet another kind of message from the sky. These are high-energy particles, mostly protons and atomic nuclei, that travel through space and occasionally strike Earth's atmosphere. When they do, they produce showers of secondary particles that can be detected on the ground or in specialized instruments. Many cosmic rays come from the Sun or from ordinary astrophysical processes, but the highest energy cosmic rays are far more difficult to explain. Their energies are so enormous that only the most extreme cosmic environments seem capable of producing them. Possible sources include supernova remnants, active galactic nuclei gamma ray bursts, and magnetized shock regions around violent objects. Yet tracing their origins is difficult because charged particles do not travel in straight lines through cosmic magnetic fields. By the time they reach Earth, their paths have been bent and scrambled. The result is a mystery made of arrival without clear return address. Gamma-ray bursts represent some of the most violent outbursts known in the universe. For a brief time, a single gamma-ray burst can outshine entire galaxies in high-energy radiation. Some are associated with the collapse of massive stars into black holes. Others appear linked to the merger of neutron stars. These broad categories are supported by growing evidence, yet important details remain unresolved, including the exact structure of the jets, the role of magnetic fields, and the diversity of burst behavior. These events matter not only as explosions but as laboratories for extreme physics. They involve relativistic motion, intense gravity, nuclear matter, and radiation processes that are difficult or impossible to reproduce elsewhere. Even when the source class is broadly known, the detailed mechanism remains a frontier. The same is true of active galactic nuclei and quasars, where matter falling towards supermassive black holes can produce enormous luminosity jets, extending across vast distances and variability across many wavelengths. Science understands the broad picture of accretion and jet formation, but not every fine detail of how magnetic fields, plasma flows, and black hole spin combine to create the observed extremes. What makes these signals especially powerful is that they arrive as clues from environments humans cannot touch directly. A burst of radio waves, a pulse of X-rays, a shower of particles, or a ripple in space-time can carry information across billions of years and unimaginable distances. The universe communicates through traces, and astrophysics learns to listen by building detectors for forms of signal that human senses never evolved to perceive. Yet listening does not guarantee full understanding. Some signals repeat without revealing their engine. Some arrive once and vanish. Some are clearly produced by known classes of object, but under conditions whose inner details remain obscure. The violent sky is therefore not chaotic in the sense of meaninglessness. It is structured, physical, and lawful. But it is also incomplete in explanation. Each flash pulse and particle shower hints at deep processes involving gravity-magnetic fields, dense matter and high energy, in combinations that still challenge theory. The universe does not reveal its most extreme regions by allowing direct approach. It reveals them by sending out fragments of consequence. A brief burst in radio light, a sudden rain of particles, or a pulse from a spinning remnant may be all that reaches Earth. From those fragments, science reconstructs entire cosmic dramas. Much has been learned, but the reconstruction is still unfinished. The violent sky continues to speak in brilliant interruptions, and many of its messages remain only partly translated. After the violent signals of the sky, the path inward returns to a quieter and more intimate mystery, the appearance of life from matter that is not itself alive. Few questions in science are as familiar and as unresolved as this one. Living things are made of ordinary ingredients. The atoms in cells are the same kinds of atoms found in rocks, oceans, clouds, and stars. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and trace elements follow the same physical laws everywhere. Yet at some point in Earth's early history, chemistry crossed a threshold. Molecules did not merely react. They began to store information, copy patterns, harvest energy, maintain boundaries, and change over generations. Matter became organized in a way that gave rise to metabolism, heredity, and evolution. Science has explained many parts of life once it is already present, but the passage from non-living chemistry to the first living systems remains one of its most difficult unsolved problems. Earth forms about 4.5 billion years ago, and evidence suggests that life appears relatively early in planetary history, perhaps within a few 100 million years after conditions become suitable. This implies that the origin of life may not require impossibly rare circumstances, though no one yet knows whether it was easy, difficult, or unique. The early Earth is not fully recoverable in detail. Its rocks have been altered, recycled, and erased by time, and so the exact environment in which life begins remains uncertain. Several plausible settings have been proposed. Some researchers look to shallow pools or tidal flats, where wet and dry cycles could help concentrate molecules and encourage complex reactions. Others focus on hydrothermal vents on the ocean floor, where mineral-rich fluids, chemical gradients, and protected microenvironments could provide a steady source of energy. Still others consider volcanic regions, ice-covered environments, or combinations of several settings over time. The mystery may not belong to one place alone, but to a chain of environments that together guide chemistry toward biology. One major challenge is the formation of the basic building blocks of life. Experiments have shown that under some conditions, simple molecules can give rise to amino acids, nucleobases, and other organic compounds important for living systems. Meteorites also contain complex organic molecules, suggesting that prebiotic chemistry is not limited to Earth. The universe appears capable of producing some ingredients of life rather widely. Yet ingredients are not enough. A pile of letters is not a language, and a pool of organics is not a cell. The deeper puzzle is how molecules become organized into systems that can sustain themselves and reproduce with variation. Among the leading ideas is the RNA world hypothesis. RNA is a molecule that can store information somewhat like DNA, but can also sometimes act as a catalyst helping chemical reactions proceed. This dual role makes it attractive as a candidate for an early stage of life before the modern division of labor among DNA, RNA, and proteins fully emerges. If early Earth chemistry could produce RNA or a related molecule, and if that molecule could copy itself with enough fidelity to persist, yet enough error to evolve, then natural selection might begin before true cells in the modern sense exist. This is an elegant idea, but important difficulties remain. It is not easy to generate long and functional RNA molecules under realistic prebiotic conditions. It is also not clear whether RNA is the first such molecule or whether some simpler informational system comes before it. Another approach emphasizes metabolism before genetics. In this view, the first step toward life may not be self-copying information, but networks of chemical reactions that sustain themselves using environmental energy. Mineral surfaces, metal ions, and naturally occurring chemical gradients might support cycles that become increasingly complex and organized. Over time, such systems could incorporate informational molecules and move toward true heredity. This picture has appeal because living cells today depend deeply on metabolism, on structured flows of energy and matter, not just on stored instructions. But metabolism without heredity may struggle to evolve in the full Darwinian sense, and so the relationship between these two possible beginnings remains unresolved. The origin of the cell boundary is another major problem. Life as now known depends on compartments. A cell membrane separates inside from outside, allowing chemistry to be concentrated, protected, and regulated. Without such a boundary, useful molecules may diffuse away before stable organization can emerge. Fatty molecules can spontaneously form vesicles under some conditions, creating simple, membrane-like structures. This suggests that primitive compartments may arise naturally. Yet building a system in which a membrane, a metabolism, and an information-bearing process all support one another is much more difficult than forming any one part alone. Life requires not just pieces but integration. The timing of this integration remains mysterious. There is also the issue of chirality, the handedness of molecules. Many biological molecules exist in forms that are mirror images of one another, but life on Earth strongly favors one-handed form over the other in important cases. Why this preference emerges remains uncertain. It may reflect chance amplified by feedback, subtle physical influences, or environmental sorting processes on the early Earth, or even before Earth forms. This question alone does not solve the origin of life, but it shows how many layers of chemical order must align before biology takes shape. Some scientists consider whether life begins not with a single dramatic event but as a continuum. In that view, there may be no sharp dividing line between non-life and life, only a gradual increase in organization, persistence, and evolvability. Certain chemical systems may become almost alive before becoming fully alive by later standards. This is a useful perspective because it softens a false demand for one magical moment. Yet even on a continuum, the emergence of open-ended evolution remains special. Once systems can reproduce imperfectly, and selection can refine them, chemistry enters a new historical regime. Patterns no longer exist only in the present. They begin to accumulate through time. Biology starts when matter acquires memory across generations. Despite decades of progress, no laboratory has yet produced a fully convincing step-by-step origin of life, from simple starting conditions under accepted early Earth realism. This does not mean the problem is impossible. It means the path is intricate. Many pieces have been demonstrated in isolation. Organic molecules can form, membranes can self-assemble, some catalytic and self-copying behaviors can occur, energy gradients can drive useful chemistry, but the complete bridge remains unfinished. The origin of life is therefore both a chemical puzzle and a systems puzzle, It asks not only what molecules can exist, but how cooperation among molecules becomes stable enough to outlast the moment. Somewhere on the early Earth, matter begins to do more than react. It begins to persist, adapt, and inherit. It begins to turn the blind grammar of chemistry into the first rough sentences of biology. Science has traced many of the letters, but the first full sentence remains unknown. Once the mystery of life's beginning on Earth comes into view, the question naturally widens beyond this one planet. If ordinary matter can organize into living systems here, under the light of one middle-sized star in one galaxy among billions, then it becomes difficult to avoid a larger possibility. Life may not belong to Earth alone. The universe contains an enormous number of stars, planets, moons, chemical environments, and spans of time long enough for slow processes to unfold. In recent decades, astronomy has transformed this possibility from a philosophical guess into a scientific field. Thousands of planets have been detected around other stars. Some are rocky. Some orbit within regions where temperatures may allow liquid water at the surface depending on their atmospheres. Some exist in systems very different from the solar system, with giant planets close to their stars, compact chains of worlds, or unusual orbital arrangements. The sky has changed from a backdrop of distant suns to a landscape of potential worlds. Yet for all this progress, no confirmed evidence of life beyond Earth has been found. The universe appears rich in opportunity but still silent in proof. This silence is especially striking because many ingredients associated with life seem widespread. Water exists in many forms throughout the solar system and beyond. Ice is common on moons, comets, and interstellar grains. Organic molecules have been detected in molecular clouds, meteorites, comets, and protoplanetary disks. Carbon chemistry appears not to be rare. Planets themselves also seem abundant. Current evidence suggests that planets may be more common than stars. This means that habitable environments broadly defined may number in the billions within the Milky Way alone. Some of the most intriguing nearby targets are not distant exoplanets, but worlds within the solar system. Mars preserves signs that liquid water once flowed on its surface, and perhaps still exists underground in some form. Europa, a moon of Jupiter, appears to hold a deep ocean beneath its icy crust. Enceladus, a moon of Saturn, sends plumes of water vapor and ice into space, carrying salts and organic compounds from a subsurface ocean. Titan has rivers and lakes, though made of hydrocarbons rather than water, and an atmosphere rich in chemistry. These worlds do not prove that life exists elsewhere, but they show that potentially life-friendly environments are not confined to Earth. The range of possible habitats may be wider than once assumed. Even so, habitability is not the same as inhabitants. A world may possess liquid water, chemical ingredients, and energy sources, yet still remain lifeless. No one yet knows which steps in the emergence of life are easy, and which are extraordinarily rare. It may be that simple microbial life appears readily wherever conditions allow. It may be that the origin of life requires a chain of accidents so improbable that it almost never happens. It may also be that simple life is common while complex multicellular life is rare, or that intelligence capable of technology is rarer still. Earth alone cannot answer these statistical questions because it offers only one confirmed example. That is both a treasure and a limitation. The search for life beyond Earth therefore proceeds along several lines. One approach studies biosignatures, signs that a planet's atmosphere or surface chemistry may have been shaped by living activity. On Earth, for example, oxygen in large quantities is strongly linked to biology, especially photosynthetic organisms. Methane can also be biologically produced, though it has non-biological sources as well. A combination of gases far from chemical equilibrium may be suggestive of life, if no simpler explanation fits. Future telescopes may be able to study the atmospheres of Earth-sized exoplanets in greater detail, looking for such patterns. Yet interpretation will be difficult. A single gas rarely serves as proof. Planetary atmospheres are shaped by geology, radiation, chemistry, and stellar behavior as well as biology. False positives and false negatives are both possible. A lifeless planet may mimic biological signals. A living planet may fail to produce obvious atmospheric clues. Another approach is the search for technosignatures, evidence not of life in general, but of technology such as artificial radio transmissions, unusual light patterns, industrial pollutants, or large-scale engineering. The search for extraterrestrial intelligence has pursued this possibility for decades, mostly by listening for narrowband radio signals or other anomalies unlikely to arise naturally. So far, no signal has been confirmed as artificial and extraterrestrial. This absence has given rise to one of the most famous questions in astrobiology and cosmology, often called the Fermi paradox. If the universe is so old and so full of stars and planets, and if technological civilizations are not exceptionally rare, then why is no clear evidence of them visible? Why is the sky not obviously inhabited? The paradox is not a formal contradiction, but a tension between apparent opportunity and observed silence. Many possible resolutions have been proposed. Intelligent life may be extremely rare. Civilizations may be short-lived. Interstellar travel may be too difficult or too slow to leave widespread traces. Technological societies may choose not to broadcast, or may use communication methods humans do not search for effectively. Life elsewhere may remain microbial, aquatic, subterranean, or otherwise quiet. Humans may also be searching in too narrow a way, over too short a period with too little sensitivity. The silence may be meaningful, or it may simply reflect how little has truly been examined. There is also the possibility that life elsewhere is built differently from life on Earth. Most scientific discussions begin with water-based carbon chemistry, because it is the only known chemistry of life, and because carbon is exceptionally versatile. But alternative biochemical pathways have been imagined involving different solvents, different energy strategies, or environments that human intuition once dismissed as too cold, too dark, or too chemically unusual. Science must remain careful here. Imagination is useful, but not all imaginable chemistries are realistic. Even so, the variety of planetary environments now known encourages humility. Earth may be one successful solution among several, not necessarily the only template life can follow. The search for alien life therefore sits in a delicate balance between abundance and uncertainty. The cosmos seems full of ingredients, full of planets, full of time, and full of environments where chemistry can become complex. Yet complexity is not enough. Somewhere beyond chemistry lies biology, and beyond biology may or may not lie intelligence, culture, and technology. Science has not yet crossed that observational threshold. It has found promising worlds, ancient water, organic molecules, and subsurface oceans. It has learned that the solar system itself may still contain hidden habitats. It has shown that the Milky Way is rich in planets, but it has not yet found a microbe in Martian soil, a cell in the ocean of Europa, a biosignature beyond reasonable doubt in an exoplanet atmosphere, or a message rising clearly above cosmic noise. Life beyond Earth remains one of the most inviting mysteries in science, because it feels both distant and near. It may exist beneath nearby ice, in ancient rocks, in a distant atmosphere, or nowhere within reach at all. The universe offers many places where life could be. Whether it has chosen more than one remains unanswered. From the search for life beyond Earth, the path inward turns toward the most immediate mystery of all, the fact that experience exists at all inside the physical universe. Rocks persist, stars burn, cells metabolize, brains process signals, store memories, and guide behavior. But within at least some living systems, there is also subjective awareness, the felt presence of sights, sounds, pain, color, thought, and the simple fact of being. Science can study behavior from the outside. It can record neural activity, trace pathways, model decision-making, and identify correlations between brain states and conscious states. Yet the inner light of experience, what it feels like to be aware, remains one of the hardest problems in all of inquiry. Consciousness is not mysterious because it is rare in daily life. It is mysterious because it is so constant and intimate that its existence is often taken for granted even while its nature remains unexplained. In broad scientific terms, consciousness refers to awareness, the presence of subjective experience. A person who is awake, perceiving, feeling, and aware of being present is conscious in a way that a stone is not, and a sleeping, dreamless body may not be. This sounds simple until the question is asked more precisely. How does a physical brain produce an inner point of view? Nerve cells communicate by electrical and chemical signals. Large networks of neurons synchronize, compete, and cooperate. Information is integrated across different brain regions. These processes can be measured, yet none of them described from the outside seems obviously identical to the redness of red, the sting of pain, the tone of music, or the private presence of thought. This gap between objective description and subjective experience is what gives the mystery its force. Neuroscience has made major progress in identifying the conditions associated with consciousness. Certain patterns of brain activity tend to accompany wakeful awareness. Damage to particular regions can alter perception, selfhood, memory, or the ability to report experience. Anesthesia changes large-scale neural coordination in reliable ways. Sleep coma seizures and disorders of consciousness all reveal that awareness is linked to the physical state of the brain. This evidence strongly supports the view that consciousness depends on biological processes, at least in human beings. If the brain is altered deeply enough, consciousness changes with it. This dependence is not really in doubt. What remains uncertain is the nature of the relationship. Dependence alone does not equal explanation. A radio depends on its circuits to produce sound, but knowledge of dependence is not the same as a full account of how signal becomes music. One family of theories emphasizes integration. In this view, consciousness may arise when information is not merely processed in separate local circuits, but woven into a unified system with rich causal structure. Integrated information theory is one example of this approach. It proposes that consciousness corresponds in some form to the degree and structure of integrated information within a system. This is an ambitious idea because it attempts to link subjective experience to a measurable property of organization. Yet it remains controversial both in its mathematical form and in its philosophical implications. Another major approach, global workspace theory, suggests that consciousness arises when information becomes globally available across many specialized brain systems, allowing perception, memory, reasoning, and action to be coordinated. In this picture, conscious contents are those that gain access to a kind of functional broadcast network. This idea has strong connections to cognitive science and to experiments on attention and report. It helps explain why only certain information enters awareness while much else remains unconscious. Still, even if such theories explain the functions of conscious access, critics ask whether they fully explain why there is any subjective feel attached to the process. This is where the distinction between the easy problems and the hard problem of consciousness often appears. The easy problems are not truly easy in practice, but they concern functions that can, in principle, be studied objectively, such as discrimination, attention, memory integration, verbal report, or behavioral control. The hard problem concerns why these functions are accompanied by felt experience at all. Why should processing information be like something from the inside? Why is there an inner movie rather than only complex behavior? Some philosophers argue that this gap may reflect a limitation in present concepts rather than an impossible divide in nature. Others think it marks a genuine explanatory challenge unlike any other in science. A further difficulty lies in identifying where consciousness begins and ends. Humans clearly possess it in a rich form. Many animals almost certainly possess at least some degree of subjective experience, especially mammals and birds with complex nervous systems and flexible behavior. But what about octopuses, insects, or simpler organisms? What about artificial systems in the future? If consciousness depends on certain functional or informational properties, then its boundaries may not align neatly with familiar categories. Yet if it depends on specific biological details, then non-biological systems may never share it. Science has not resolved this. The question matters not only for theory but for ethics, because it shapes how suffering awareness and moral value are understood across living beings and perhaps beyond them. This sense of self adds another layer of mystery. Consciousness does not always appear as pure perception alone. It often includes a center, a feeling that experience belongs to someone. Yet neuroscience suggests that the self is not a simple indivisible entity located in one place in the brain. It may be constructed from many processes: body mapping, memory, attention, prediction, social modeling, and narrative continuity. Injury, illness, and altered states can fragment this sense of self in striking ways. People can feel detached from their own bodies, fail to recognize a limb as their own, lose autobiographical continuity, or experience divided awareness after major neural changes. This suggests that the self is built, not given in fixed form. But if the self is constructed, the existence of subjectivity itself still remains. Even when the story of self is altered, something is still present to undergo the alteration. There is also the question of whether consciousness plays a causal role or is simply an accompaniment to brain processes. Human intuition says it matters. Pain motivates withdrawal. Thought guides decision. Deliberation seems to affect action. Yet some philosophical positions have suggested that subjective experience could be epiphenomenal, real, but causally secondary, like a shadow cast by deeper mechanisms. Most working scientists do not adopt such a view in practical research, but the question reflects how incomplete the conceptual framework still is. Consciousness sits at an intersection of neuroscience, psychology, philosophy, computation, and biology. Science can increasingly map the neural correlates of awareness. It can distinguish different conscious states, alter them, and sometimes restore them. It can model perception, attention, and memory with growing detail. But the core mystery remains. How does organized matter become experience? How does a brain built from cells and chemistry open into a world of colors, sounds, feelings, and thought? The human mind is the instrument through which all science is known, yet the nature of that instrument's inner light remains obscure. Consciousness is not hidden in the sky or buried beneath the sea. It is present in the act of noticing. That intimacy makes it harder, not easier to explain. Science has learned much about the brain's machinery, but the fact that machinery is accompanied by awareness still stands as one of its deepest unanswered questions. Within consciousness itself, there is another landscape of mysteries, one that feels closer than distant galaxies and yet remains difficult to map with certainty. Human beings do not simply remain awake and aware in a steady, unchanging way. The mind drifts, dreams, remembers, misremembers, imagines, fears, anticipates, and sometimes experiences strange moments in which time seems to slow, repeat, or loosen its usual structure. Emotion colors perception. Memory reshapes the past each time it is recalled. Creativity draws connections that did not seem present before. Familiar places suddenly feel uncanny. A face, a scent, or a fragment of music can release an entire buried atmosphere from years earlier. The inner world is active even in stillness, and many of its most ordinary features remain only partly understood. Dreams are among the most familiar of these mysteries. Nearly everyone experiences them, yet their purpose remains uncertain. During sleep, especially during rapid eye movement sleep, the brain can produce vivid scenes, emotions, narratives, and sensations without direct input from the external world. Some dreams are fragmented and quickly forgotten. Others are so intense that they linger through the day. Neuroscience has identified patterns associated with dreaming, including activity in visual, emotional, and memory-related brain systems. But why the brain constructs dream experience in the first place is still debated. One view holds that dreams help process memory and emotion, integrating recent experiences into broader networks. Another suggests they reflect the brain's spontaneous effort to generate predictive simulations from stored patterns. Some theories emphasize rehearsal of threats or social situations. Others treat dreams as a byproduct of brain activity during sleep, meaningful only because waking minds impose meaning afterward. None of these explanations fully settles the matter. Dreams may serve several functions at once, or they may arise from mechanisms whose original purpose is not identical to the narrative experience itself. Memory is no less mysterious. It often feels like storage, as though the past is placed somewhere in the mind and later retrieved intact. Yet research shows that memory is not simple recording. It is reconstructive. Each act of recall can modify what is remembered. Details are strengthened, weakened, altered, or woven together with newer interpretations. Emotional states shape what is encoded and what is later recovered. Attention influences which moments become durable at all. Some memories remain vivid for decades while others disappear within hours. The brain does not keep every event with equal loyalty. It selects compresses, rearranges, and sometimes invents. This reconstructive quality is not a flaw added onto memory. It may be part of what makes memory useful. A system built only for exact archival storage might not support flexible reasoning, planning, and adaptation, as well as one that extracts patterns and meanings. Yet this usefulness creates uncertainty. People can be certain of things that did not occur as remembered. False memories can arise through suggestion repetition, or the blending of real fragments into imagined wholes. The boundary between recollection and construction is often less firm than subjective confidence suggests. Time perception adds another layer of instability to the inner world. Physical clocks measure time with extraordinary precision, but experience time stretches and contracts depending on context. A frightening moment may seem prolonged. A repetitive afternoon may feel slow while it unfolds, but strangely empty in retrospect. A rich and absorbing period can pass quickly in the moment, yet appear substantial in memory. Childhood summers often feel long in recollection, while adult years can seem to accelerate. Neuroscience and psychology link time perception to attention, novelty, emotional arousal, bodily rhythms, and memory density, yet no single account explains all its variations. The mind does not simply observe time, it actively constructs temporal experience from internal and external cues. This means that the felt flow of life is partly a product of perception, not just a direct reading of the world. Emotion shapes nearly every aspect of this internal landscape. Fear narrows attention toward threat. Grief changes the texture of time and memory. Joy alters perception, motivation, and social connection. Shame, awe, attachment, anger, and tenderness all influence not only what is felt but what is noticed, remembered, and imagined. Science has learned much about the brain systems involved in emotion, including the roles of structures such as the amygdala, insular, prefrontal cortex, and networks linking bodily signals with interpretation. Yet the full nature of emotion remains complex because emotions are not simple inner objects. They involve physiology, appraisal, learning culture, and meaning. An emotion is both a bodily event and a way of organizing the world. It is chemistry and interpretation together. Creativity is similarly difficult to reduce. New ideas often appear less like deliberate construction and more like emergence. A solution forms after a period of rest. A melody arrives before its logic is clear. A scientific insight appears when separate facts suddenly align into a pattern. Research connects creativity to memory recombination, associative flexibility, attention shifts, and cooperation between brain networks involved in focus and mind wandering. Still, the felt arrival of a new idea often retains an element of surprise. The mind seems capable of preparing patterns beneath awareness and presenting them later as insight. This is not supernatural. It is one of the ordinary powers of a complex predictive brain. Yet its timing and texture remain striking. Déjà vu offers a small but haunting example of this complexity. In such moments, a present situation feels strangely familiar, as though it has already happened even when it clearly has not. This sensation is usually brief, but it can be powerful. One possibility is that it reflects a mismatch between systems involved in familiarity and detailed recollection. A situation may trigger the feeling of prior experience without the actual recovery of a matching memory. Other explanations involve processing delays, partial pattern overlap, or subtle neural timing effects. The experience is common enough to be familiar, but not so common or predictable that it is fully domesticated by explanation. The mind occasionally misfires in ways that reveal the seams of its construction. Even ordinary waking thought contains large regions outside deliberate control. Minds wander, associations unfold, internal speech continues, attention shifts toward concerns not consciously chosen in the moment. The resting brain is not inactive. It remains busy integrating memory, projecting futures, simulating social scenes, and maintaining a narrative sense of self across time. Much of mental life therefore occurs at the edge of awareness or beneath it. Consciousness may feel like a centered stage, but much of the production happens off-stage with only selected results arriving in clear view. This inner uncertainty does not make the mind irrational in a simple sense. It makes it layered. Human beings live partly in the present, partly in recollection, partly in anticipation, and partly in emotional weather that changes what the present means. Science has traced many of the mechanisms involved in dreaming, remembering, feeling, and imagining. It can identify brain states associated with sleep stages, emotional arousal, and memory consolidation. It can show how recollection is reconstructed, and how perception of time depends on attention and context. Yet the total choreography remains incomplete. The inner world is lawful but not transparent. Dreams still drift through sleep without full explanation. Memories keep changing while preserving identity. Emotion continues to color thought from within. Creativity rises from networks that know more than awareness can immediately say. The mind contains not only consciousness, but weather within consciousness, and much of that weather remains mysterious. At the boundary between inner experience and bodily life, another cluster of mysteries gathers around sleep aging and the limited ability of living things to renew themselves. These processes are so familiar that they can seem almost ordinary. Every day, consciousness fades into sleep and rises again. Every year, the body changes in ways that gradually accumulate. Wounds close, tissues repair, cells divide, and yet the larger arc still moves toward decline. Some organisms regenerate astonishingly well, others age quickly. Human beings do both repairing constantly and deteriorating slowly at the same time. Science has uncovered many mechanisms involved in these processes, yet the central question remains unresolved. Why must complex animals like humans spend so much of life asleep? And why does the living body, despite all its powers of maintenance, ultimately grow old? Sleep is one of the strangest universal behaviors in biology. It leaves an animal vulnerable, unresponsive, and unable to pursue food mates or immediate goals. From the outside, it looks costly. Yet sleep is conserved across an enormous range of species, which suggests that whatever it provides must be deeply important. The brain does not simply switch off during sleep. Different stages of sleep show different patterns of activity. In some phases, slow, synchronized waves pass across large brain regions. In rapid eye movement, sleep brain activity can resemble waking states in certain respects, while vivid dreams become common and muscle tone is greatly reduced. These changing states suggest that sleep is not one thing, but several coordinated processes. Research indicates that sleep supports memory consolidation, emotional regulation, metabolic balance, immune function, and cellular maintenance. During sleep, recently encoded experiences may be replayed and integrated into longer-term memory. Emotional experiences may be processed in ways that help stabilize later waking function. Metabolic byproducts may be cleared more efficiently from the brain. Hormonal rhythms tied to repair growth and energy balance follow sleep-linked cycles. Yet even with all these discoveries, sleep still resists full explanation. It is possible to describe many benefits of sleep without fully knowing why such benefits require a state so globally disruptive to waking behavior. One of the most interesting findings in recent years concerns the brain's waste clearance systems. During sleep, especially deep sleep, the movement of fluid through brain tissue appears to change in ways that may help remove metabolic waste products. This has led to the idea that sleep serves an important housekeeping function for the brain-clearing substances that accumulate during waking activity. The idea is plausible and supported by growing evidence, yet it is unlikely to be the whole story. Sleep affects too many systems to be reduced to one single purpose. It may be better understood as a recurring biological state that allows multiple forms of restoration and reorganization that waking life cannot easily provide. Even so, the deepest question remains: why should an organ as important as the brain require periodic withdrawal from the waking world in order to remain functional? Why was evolution unable to solve these needs in a fully waking mode? The answer is still incomplete. Aging presents a related but even broader mystery. At one level, aging is familiar in outline. Cells accumulate damage. DNA suffers breaks and mutations. Proteins misfold. Mitochondria become less efficient. Stem cell reserves change. Immune responses alter. Tissues lose elasticity, coordination, and resilience. These processes do not unfold at identical rates in every organ or every individual, but together they produce the gradual decline associated with age. Science has identified several hallmarks of aging patterns that recur across many organisms and link cellular damage to larger physiological deterioration. Yet knowing the mechanisms is not the same as knowing why aging exists in the first place, or why it unfolds in the particular way it does. From an evolutionary perspective, aging may reflect the fact that natural selection is strongest on traits that affect early survival and reproduction. Harmful effects that emerge later in life may be less effectively removed by selection, especially if genes that help early reproduction carry costs in later years. This idea, sometimes called antagonistic plecotropy, helps explain why bodies are not built for indefinite maintenance. Another view emphasizes disposable soma theory, the idea that organisms allocate limited energy between reproduction and long-term repair. Perfect maintenance may be too costly in evolutionary terms compared with successful reproduction. These ideas are powerful, but they do not make aging feel simple. They explain why evolution may tolerate deterioration, not why deterioration must take the exact biological forms it does. The mechanisms of aging are also deeply interconnected. Damage to DNA affects gene expression. Gene expression affects protein maintenance. Mitochondrial decline affects energy production and oxidative stress. Cellular senescence, a state in which cells stop dividing but remain metabolically active, can protect against cancer in some contexts, while contributing to inflammation and tissue dysfunction in others. Inflammation itself, especially chronic low-grade inflammation, becomes a major feature of aging bodies. The result is not one clock, but many overlapping clocks interacting across scales from molecule to tissue to whole organism. Some interventions in animals can extend lifespan or improve health span, the period of life spent in relatively good health. Caloric restriction, altered nutrient-sensing genetic changes, and certain drugs affect aging-related pathways in model organisms. This shows that aging is not an unchangeable fate unfolding at a fixed rate. It is biologically adjustable, at least to some degree. Yet these findings do not amount to a final answer. Extending life in simple organisms does not translate directly into mastery over human aging, and increasing lifespan alone is not the same as preserving full physical and cognitive vitality. Regeneration reveals an even sharper contrast. Some animals can regrow lost limbs, repair major injuries, or even rebuild large portions of the body. Salamanders can regenerate limbs. Certain flatworms can regrow extensive body structures from fragments. Many simpler organisms show powers of renewal that humans lack. Human beings can heal cuts, mend bones, and renew some tissues well, but they cannot regrow an arm or fully repair severe damage to the spinal cord or heart in the way some other organisms can. Why evolution preserves dramatic regenerative ability in some lineages while limiting it in others remains uncertain. One possibility is that the demands of complex body plans, cancer suppression, immune defense, and scar-based rapid closure create trade-offs that favor safer but less complete repair. Another is that regenerative potential still exists in part but is tightly suppressed or redirected by developmental controls. Research into regeneration therefore carries a dual mystery: how other organisms accomplish it, and why humans do not. The body then is neither fragile in a simple sense nor endlessly self-renewing. It is a temporary structure of remarkable maintenance that nonetheless cannot maintain itself forever. Sleep restores it daily, but not permanently. Repair operates continuously, but with limits. Aging proceeds not because life is passive, but because active maintenance is never perfect, and may never have been selected to be perfect. Science has illuminated many of the pathways involved, yet the whole remains unresolved. Why consciousness must repeatedly disappear into sleep why the body yields to time despite constant repair, and why some living beings regenerate so much more fully than humans do, are questions that remain partly open. Life preserves itself with extraordinary devotion but not complete victory. At this boundary between survival and decline, biology still keeps some of its deepest secrets. At the innermost edge of this journey after the cosmos, the first life, the hidden mind and the aging body, the remaining mysteries gather around the qualities that feel most distinctly human. Language, laughter, music, love, tears, moral feeling, symbolic thought, and the strange ability to ask questions that may never be fully answered, all emerge from the same biological world that produces bone, blood, and nerve tissue. None of these traits stands entirely outside animal life. Other species communicate, bond, grieve, play, and display forms of intelligence. Yet in human beings, these capacities combine into something unusually expansive. They produce culture, science, art, law, memory across generations, and elaborate inner worlds shared through symbols. Science can study many parts of this richness, but the complete reason these particular forms of human nature take shape as they do remains incomplete. Language is among the clearest examples. Human language is not just a set of sounds linked to immediate needs. It is recursive, open-ended, and capable of referring to things absent, abstract, imaginary, or impossible. It allows minds to share not only information but models of the world. With language, experience becomes portable across time. A thought formed in one brain can be preserved, reshaped, and revived centuries later in another. Neuroscience, linguistics, cognitive science, and evolutionary biology have all illuminated parts of this capacity. The brain contains networks important for speech production, comprehension, syntax, memory, and social interpretation. Children acquire language with astonishing speed under ordinary conditions. Human vocal anatomy and auditory processing support rich sound-based communication, while sign languages show that gesture can carry equally complex structure. Yet the origin of language in evolution remains uncertain. It is not clear when symbolic communication becomes full language, or whether language begins gradually from social signaling tool use, shared attention, and imitation, or through some more abrupt cognitive shift. It is also not clear how syntax, the ordered structure that allows infinite expression from finite elements, emerges from earlier systems. Language feels natural once present, but its arrival in the history of life remains one of the great thresholds. Music is no less mysterious. Human beings across cultures produce rhythm, melody, harmony, repetition, and tonal patterning that can move emotion with great power. Music can calm, excite, coordinate movement, strengthen identity, and evoke memory more directly than many forms of speech. It activates broad brain networks involving perception, timing, expectation, reward, and emotion. Infants respond to musical structure early. Groups synchronize through song and rhythm in ways that shape collective behavior. Yet it remains uncertain why music exists in such a deep and nearly universal form. Some researchers see it as an adaptation for social bonding, parent-infant regulation, or coalition signaling. Others regard it as a byproduct of capacities that evolve for language, motor coordination, and pattern recognition. It may be both useful and more than useful, arising from older neural systems and becoming culturally elaborated into something no single evolutionary purpose can fully explain. The tears brought by music, the chills from a harmony, and the sense of meaning carried by abstract sound show that human feeling is not tied only to survival in any narrow way. Laughter and play reveal a similar ambiguity. Play appears across many intelligent animals and often supports learning, flexibility, and social development. Human laughter can signal relief, bonding, surprise, status, embarrassment, or the release of tension. Humor depends on expectation violation, interpretation, and shared mental framing. It is cognitive and bodily at once. Yet no single theory of humor explains all its forms. People laugh at incongruity, at release from tension, at the safe collapse of threat, at social recognition, and sometimes at nothing more than contagious timing. The scientific study of laughter reveals patterns but not a final essence. It is another example of a behavior that is deeply human, biologically grounded, socially powerful, and still resistant to complete reduction. Love may be the most familiar and least exhausted of these mysteries. Attachment between parent and child, between partners, between friends, and between people, joined by kinship or loyalty, has clear biological foundations. Hormones and neurotransmitters influence bonding, reward, trust, and desire. Evolution strongly favors systems that support caregiving, pair bonds in some contexts, and durable social alliances. Yet human love cannot be described only as chemistry without losing something important. It is also memory, commitment, projection, vulnerability, imagination, and meaning. It reorganizes attention and changes the felt significance of the world. Grief shows the same depth from the opposite side. When attachment is broken, the body and mind register absence, as if a structure in reality has been torn open. Science can describe the neural and hormonal dimensions of bonding and loss, but the lived fullness of love resists being contained by mechanism alone. Tears add a small but striking question. Humans cry for many reasons: pain, grief, frustration, awe, relief, tenderness, and joy. Emotional tears are unusual in the animal world as far as clear evidence shows. While human beings evolved, this visible signal remains uncertain. Tears may communicate need, sincerity, helplessness, or emotional intensity in ways that reduce aggression and increase care. They may also be partly a byproduct of how closely emotional arousal and autonomic control are linked in the human face and body. Still, the fact remains oddly specific. The species that builds telescopes and particle colliders also weeps in response to beauty, memory, and sorrow. Moral life deepens the mystery further. Human beings do not merely compete and cooperate. They judge, justify, admire, resent, punish, forgive, and imagine obligations that extend beyond immediate instinct. Moral behavior has roots in social evolution. Empathy, reciprocity, kin selection, reputation, and group living all help explain why some forms of concern for others would be favored. Yet morality in human life also becomes abstract. People can sacrifice for strangers, for principles, for imagined futures, or for truths that bring no obvious reproductive advantage. They can be cruel in the name of ideals and compassionate beyond calculation. Science can study moral cognition, emotional empathy and decision-making, but the full emergence of ethical life from biological history remains unsettled. Perhaps the most human mystery of all is the drive to seek explanation itself. The mind does not rest with appearances. It turns outward toward stars and inward toward memory. It creates mathematics, rituals, poems, maps, stories, experiments, and instruments. It asks not only how things work, but what they mean. Whether this drive is simply an elaboration of prediction and survival, or whether it marks a deeper feature of reflective intelligence, remains open. Human beings are a biological species produced by evolution, and yet they are also the part of the known universe that asks why the universe exists. That fact does not remove humans from nature. It binds them more intimately to it. The same matter that condenses in stars, circulates in oceans, forms cells, and builds nervous systems, eventually becomes capable of language, music, love, tears, and science. The mystery is not only how the universe began or how life first emerged, but how matter becomes a creature that sings, remembers, mourns, reasons, and searches for truth. Science has clarified parts of that transformation with great power. It has traced the brain systems of language, emotion, and social life. It has shown the evolutionary continuity between humans and other animals. It has revealed mechanisms behind bonding, play, communication, and moral judgment. But the whole remains larger than the parts. Human nature is not outside science, yet neither is it fully exhausted by present explanation. At the deepest inward point, the unsolved mystery is not only the cosmos above or the cell below. It is the fact that reality has produced beings able to wonder at both, and to feel that wonder as part of their own inner life. The universe remains quiet around its unanswered questions. Dark matter still holds galaxies in invisible structure. Black holes still hide their interiors behind horizons that no light can cross. Consciousness still glows within matter without yielding a final explanation. Life still stands on Earth as the only confirmed example of biology, even while countless worlds circle distant stars. Sleep still arrives each night like a necessary surrender. Aging still moves through the body despite all the labor of repair. Human beings still speak, sing, love, remember and grieve without fully knowing why these inner forms feel so meaningful from within. Science has not failed in the face of these mysteries. It has done something more subtle and more impressive. It has measured what can be measured, narrowed what can be true, and shown where ignorance is honest rather than empty. It has revealed that mystery is not the absence of knowledge, but the edge of it. Beyond that edge, questions remain not because reality is chaotic, but because it is deep. The stars continue above the sleeping world. The mind continues within the resting body. Between them lies a long chain of things partly understood and partly hidden, from atoms to thought, from cosmic expansion to memory, from ancient light to the brief warmth of human feeling. Nothing in that chain is separate. The same universe that scatters galaxies across darkness also gathers matter into cells, brains, language, and wonder. And so the unsolved mysteries of science do not sit far away from ordinary life. They are folded into existence itself, into time, into being awake, into being alive. They remain quiet and unfinished as the world grows still.